Hi everyone, this is Dr. K. Kannan, Associate Professor, Department of EC, RMK College of Engineering and Technology. So in this lecture video, I am going to discuss about the importance and the characteristics of optical diode, optical detector in the receiver. So what are the basic requirements for any photodetector or photodiode? It is compatible with the physical dimension. It should be very small size. Then low sensitivity and high responsivity at the desired wavelength and low responsivity elsewhere wavelength selectivity. Low noise and high gain. Fast response time, high bandwidth, insensitive to the temperature variations and long operating life and low cost. Then photodiode. So photodiodes meets most of the requirements, hence widely used as a photodetector. So positive, intrinsic, negative. That is PIN photodiode, no internal gain, robust detector. And another one, it is a photodiode in terms of avalanche photodiode, where advanced version with the internal gain M due to self-multiplication process. Photodiodes are sufficiently reverse biased during normal operation. So no current flow without illumination. The intrinsic region is fully depleted by the charge carrier. So the principles of photodiode. The photodiode is in fact a PN junction put into the exact opposite use of the LED. The variation in current is a function of the incident light. Use of the stimulated absorption of light by semiconductor material for the generation of electron hole pairs. The energy of the observed photon to transfer the electron from the ground to the excited state contributes to the variation in circuit current. The energy of the observed photon must at least be equal to the bandgap material for the material to respond to the incoming photon. Now, what is the physical principles of photodiode? A simple way to increase the depletion region width is to insert a layer of undoped or lightly doped semiconductor material between PN junction in the normal PN diode. Since the middle layer consists of nearly intrinsic material, such as structure is referred to as a PIN photodiode. When photons enter into the photodetector, the low bandgap absorption layer absorbs the photon and an electron hole pairs are generated. This electron hole pairs is called photocarrier. So these photocarrier under the influence of a strong external electric field generated by a reverse bias potential difference across the device as shown in figure produce photocurrent proportional to the number of incident photon. So the basic principle of photodiode, as a photon flux of pi penetrates into the semiconductor, it will be observed as it progresses through the material. So therefore, the level at a distance x into the material p of x is equal to Pn into e power minus alpha s into x. So the observed photon trigger photocurrent Ip in the external circuitry. So this gives to rise the current flow in an external circuit is known as photocurrent. So look at the diagram of pin photodiode. So in between P and N, there is a layer is sandwiched between P and N type material that is called intrinsic layer, where when you are going to apply external field by the bias voltage, the negative potential to the P and a positive potential to N via load resistor. Now look at that the power level and the distance is going to be a decreased to 1. This is the energy band diagram for pin photodiode. So initially there is a photo generated hole. When you are going to have the external supply, then it is jumping from lower energy level to high energy level. So there you are going to get the electron recombination so that the energy is released. Then the electrons coming from the higher energy level to lower energy level by sending some output. So you can measure the this wavelength, the cutoff wavelength lambda c by the formula Hc by Eg. For an example, we can do one problem. A photodiode is constructed of gallium arsenide, which has a band gap energy of 1.43 electron volt at 300 Kelvin. What is the cutoff wavelength lambda c? Lambda c is equal to Hc by Eg. So we know the value of H is a Planck's constant and C it is a constant. Eg it is a 1.43 into 1.6 into 10 power minus 19 joule per Kelvin. So finally we can get lambda c equal to 869 nanometer. Then what is the photocurrent? So as already discussed, P of x is equal to P naught into 1 minus e power minus alpha x lambda x, where lambda c is equal to 1.24 divided by Eg into electron volt. So taking the entrance phase reflectivity into the consideration, the observed power in the width of the depletion region W becomes 1 minus RF into P of W is equal to P naught into 1 minus E alpha Z lambda omega into 1 minus RF. Then the diffusion length, it is represent carrier moving distance Ln, or we can represent in terms of Lp for holes and electrons. Carrier lifetimes, electron or hole recombination time, it is Ln, dn tau n whole power 1 by 2. Similarly for hole, Lp equal to dp tau p whole power 1 by 2. Then what are the characteristics of photodetector? One is quantum efficient and another one responsibility. So the quantum efficiency, it is a ratio of number of electron holes per generated per number of incident observed photons. So based on the incident observed photon, how many numbers of electron holes per generated, that is called quantum efficiency. Okay, so it is given by IP by Q whole divided by P and by H. Then optical absorption coefficient, now look at that P of x is equal to P naught into 1 minus e power minus alpha s of lambda into x. This diagram shows that what is the wavelength and the corresponding light absorption coefficient in terms of 10 power 2, 10 power 3 like that. So here we have three different material, silicon, gallium arsenide and gallium. Then light absorption coefficient, the upper cutoff wavelength is determined by the energy band gap material Eg. The lower wavelength end, the photo response diminishes due to low absorption. So there is very low value of alpha S. Then the responsivity, the primary photocurrent resulting from the absorption IP equal to Q divided by H nu P naught into 1 minus e power minus alpha S of lambda W into 1 minus R. Therefore, the quantum efficiency eta equal to number of electron hole pairs generated by incident photon. So capital R equal to IP by P naught. Then this is a representation of responsivity versus wavelength, depends upon the percentage. So 10 percentage, 30, 50, 70, 90 based on the germanium, silicon, then indium, gallium arsenide. So finally we can find out the quantum efficiency. Thank you one and all.